So as mentioned, we're switching to Staffan first. Staffan Berg is of Mental Graphics. He's a Verification Solutions Applications Engineer. Staffan Berg is currently working as European Application Engineers at Mental Graphics. He specialises in digital function verification tools and methodology. He's been with Mentor since 1989, working in many different fields including real-time software development tools, simulation, logic synthesis, formal verification and hardware-software co-verification. Prior to joining Mentor, Staffan worked as systems engineer at Retargetable and as EDA tool developer at Ericsson Telecom. Staffan holds an MSc degree from the Royal Institute of Technology in Stockholm in Sweden, and the title of his talk is Automating Reusable, Retargetable Scenario Level Tests with Portable Stimulus. So I hand over to Staffan.
Thank you, Mike, and thank you for inviting me here today. I hope you can all hear me clearly. So as Mike mentioned, I have a pretty long background in verification. I was actually visiting a customer a couple of weeks ago together with one of my colleagues, Mikael Andersson, and during the meeting when we introduced ourselves, we realized that between the two of us we had more than 50 years of verification experience. I don't know if that's good or bad. It's a bit frightening anyhow. So today I'm going to talk about automating scenario level tests with portable stimulus. So obviously we're going to talk a lot about scenarios, and I'm going to try to explain what portable stimulus is and how it can help you to model and verify your scenarios. And we're going to talk a lot about reuse as well. So you're probably well aware that SOC verification is significantly different than block or subsystem level verification. At block level, everything is very much focused on transactions, individual transactions, and coverage. The goal is to generate lots of transactions to get high coverage, both code coverage and functional coverage, as quickly as possible. Now, when you move up to SOC level, the objectives change quite dramatically. At SOC level, it's simply not realistic to try to reach full coverage. Instead, people tend to focus more on interesting scenarios that needs to be verified, corner cases or situations, rather than individual transactions. And since these scenarios are much more complex and can encompass many transactions, you need to be more productive when you create them, otherwise it will take forever. Something called test intent also becomes very important, that when you develop a block level test, you do it with the intention, of course, of verifying a certain aspect or piece of functionality. And it's good if that can be reused at the subsystem level or even at the SOC level when you move up. So at the block level, UVM has been extremely successful in the last couple of years in providing a tool set for quickly generating lots of transactions, getting high coverage, which many companies use today at the block level. Unfortunately, it's not been as successful at the SOC level, and the reason is that when you move up to SOC level, you involve one or more processors running software, and UVM, as it is today, has very little provisions for expanding the tests to also involve software. So many times companies regularly use software-driven tests at SOC level, test programs running on the processor, but when they develop those tests, they start with a blank page. They can't really reuse what's done at the block level, which is, of course, a big disadvantage. So that's one dimension of reuse, going from block to subsystem to SOC. But there's also another aspect or another dimension. All companies doing advanced SOC design today, they use a whole range of different verification environments. Usually start with simulation, moving on to emulation, later on FPGA prototyping. And every time this is done, they have to more or less start from scratch. How do you take your UVM test and run it on an FPGA prototype, for example? So these are some of the difficulties that this portable stimulus methodology is trying to address. So what is a scenario? Well, scenarios are everywhere around us. This slide that my colleague actually created actually shows a flow chart that shows the process for getting a business license in Oregon. So it doesn't really apply to verification. But verification scenarios usually are built up of sequences of transactions that can be pretty long and complex sometimes. There can be different modes of operations that need to be taken into account. And usually, since it's a system, there's more than one interface, and traffic on these interfaces has to be coordinated. Today's complex design have very complex protocols. There's complex logic like queue reordering logic, processor pipelines, complex interconnects such as AMBA-ACE, for example, that has its own complex behavior. And all these are difficult to verify at the block level. You have to do system level tests, really. So how do you create a scenario? Well, even at the block level, that can be pretty hard for several reasons, because it's more complex than creating individual transactions. When you progress through a flow, like, sorry, the one we see here, there are a number of choices that needs to be made, and you have to be careful so you don't end up in a sort of dead end where there is no legal way to continue. So you have to have a tool and a methodology that can iteratively make decisions on the way to what kind of scenario that should be produced. Typically, the state space is huge, even at the block level, not to mention at the SOC level. There are billions and billions of combinations, so you can't cover everything. And that's why you need to ensure that we are sure to cover the scenarios that we're really interested in, that we don't miss them in this huge state space. And constrained random, unfortunately, is not very good at hitting those precise scenarios because of the huge state space. You may have to run constrained random forever to get to covering the scenarios we're really interested in. So you have to select a subset. What is it I'm going to verify today? What are the particular scenarios or corner cases I want to see? And then you need to migrate those from the block level to the SOC level or even higher. So let's look at a simple example. This is a PCI Express transaction layer package, a TLP. At the block level, it's pretty straightforward. We want to create and send a TLP package, then possibly inject a PCIe event, such as connecting or disconnecting a new device. So this is for a root complex in PCI Express, obviously. And then send a second TLP and make sure it still works after the event here. And we want to cover all the combination of different TLP types and link events. So how would you do that in UVM? Well, someone would have to write a UVM sequence, which requires certain skills, of course. You have to know system Verilog, you have to be familiar with UVM, you have to know PCIe. So it's very dependent on the writer's skill. And it's pretty hard for someone else to understand that people writing the tests may not be experts on the low-level details of PCIe or even UVM. So it's kind of hard just to look at the code here to understand what it's doing. So in this case, it's a UVM sequence, and we have two sequence items that we create here at the top, and then there's a forever loop. So we start the first item here, and then we randomize the event, and then we select what type of event we want to do, and then we randomize and send the other TLP package here. So it's not rocket science, but it may still be pretty hard to comprehend for someone not familiar with UVM. It's also kind of hard to control it from the outside, to constrain it and to shape traffic in a certain way, for example, without rewriting the actual code inside the sequence. And it's very difficult to reuse it in other environments, because this is very specific to a simulation environment with system Verilog. You may be able to connect it to an emulator, but there is really no way you can connect it to a real prototype, for example. There's no notion of software running on the system at all. So as soon as that comes into play, you have to redo all your tests. So if we use graph-based portable stimulus for the same example, what would that possibly look like? Here we see an example of a PCI Express scenario graph. And as you may notice, it's very similar to the simple flow chart I showed you in the beginning. So it's just a loop here that sends the first TLP, injects the event, and then the second one. So even for someone who doesn't know much about UVM or even PCIe, it's very easy to get a high-level view and understand this. And you can expand it to see the lower-level details. So here we see the 4 different types of events that we deal with, for example, here. And this whole description is made in a declarative language which is independent of the target environment. So the same description works with simulation, with emulation, even with embedded software to drive software on a processor. So our implementation of this is a tool called Questa, in fact, that uses this independent language to effectively describe scenarios at a high level. And during simulation, it is systematically traversing the graph to produce the right stimulus for the scenarios you want. It is working with a number of different target environments. So typically it can be used at block level with a UVM or OVM test bench. It also works with system C, but it can also drive embedded software running on a processor using exactly the same description, as we will see later. So this independent language I was talking about, what does it look like? Well, it's a declarative language that can capture both the data modeling aspects and the control flow and relationships between different elements. So the input is a very compact textual description that could look something like this. It's based on object-oriented technology. So here we have a struct, for example, that has 2 variables or meta actions, A and B. They can be of the typical types you would use in a test bench, integers, enumeration types, other structs, scalar and composite data types. So we declare these variables, and then we have a second struct, which is extended from my base struct, so it adds another variable. It also adds a constraint that shows an algebraic relationship between 2 of the variables. And the language also contains constructs for control flow, like sequences, repeat loops, and choices, as you can see in this graph here. So the input is this very compact text, and you can visualize the stimulus as this graph-based representation. So if we apply this to the PCIe example, this is what it could look like. So we have at the top level a repeat loop that again generates a TLP, injects an event optionally, and then creates a second TLP and sends it. And inside the event view, there is this multiple choice that you can see here. Now, there's quite a few things we can do to reuse existing verification IP from the block level. So, for example, we want to create 2 TLP items, and the TLP items are described as UVM sequence items, and those can be imported and reused directly. So all the variable declarations can be directly imported to the graph. Then we use something called an interface, which is really the key to independence here. The interface is an abstraction of the implementation of this stimulus item. So depending on the target environment, the interface gets implemented as, for example, in the case of UVM, it would be a start item, finish item function call. In the case of a embedded software environment, the interface would be translated into function calls to driver code in a library. But the actual implementation is done by the tool. And then we have a struct. The whole scenario is described as a struct. So we have two instances of the TLP here, which was imported from the UVM test bench. And then we have some actions, which are in turn just calling the existing sequences, lower level sequences, to do the event injection. So we can reuse those as well. And the whole scenario is these 4 lines at the bottom. PCI scenario is do item TLP1, inject event, do item TLP2. So really simple. So this graph that I just showed you describes the total legal input space, but it hasn't said anything about what the goals are, what are the specific scenarios that we are interested in seeing. And that's the other side of the model, the other half, which is called the coverage strategy. This is where you define the goals for the scenario, the key values, the ranges, the combinations or sequences that you're interested in seeing. And this is done by applying a layer on top of the graph that can contain things like cover points and crosses, which will then be targeted during simulation. You can put priorities on them. You can choose if you want to leave them as random or if they should be systematically explored by the tool during simulation. And the result is a very goal-driven systematic generation. So you won't keep repeating the same combinations over and over. It's going to target exactly those sequences and values and combinations that you have specified in the coverage strategy. So again, if we look at the PCIe example, to exhaustively cover every combination of TLP fields and events, the TLP itself contains an 8-bit data payload and a 16-bit address. And if you do the math, you end up with actually 6 quadrillion combinations. So that's probably going to take a couple of million years to simulate all that. So we have to refine the coverage goals. So what we can do is we're really only interested in the TLP type crossed with the other TLP type for TLP2 crossed with the event. What the actual data and addresses are doesn't matter. It's just a type. Is it a read or a write and so on. So we have done all types of TLPs. And if you do this reduction, you end up with 3,600 combinations, which is much more realistic. That's something that you can simulate in seconds or minutes. And there's no redundancy, so the completion is very predictable, how long it's going to take. You're not going to run for weeks. So the next step would be to take this one level up to create a larger, more complex scenario. Because of the object-oriented nature of the language here, it's very easy to reuse what we already have. So here I have created another scenario called PCIe back-to-back. So we're going to do 2 of these scenarios as so previously, back-to-back to one another. So we import the scenario that I just showed you, that does TLP event and TLP. And we have 2 instances of that now. And then there are specific combinations, specific types of traffics we want to look at. So we do some shaping here by adding a constraint that says, okay, the transfer type for the TLP will only be PCI IO read and IO write. So we're limiting the scope of this particular scenario, adding constraints on top of the previous scenario. And again, the actual scenario is very simple. It's just do S1, do S2, and check the coverage. And we're done. So you can see that it's very easy to hierarchically build up and reuse what you have done in one level. So by combining these 2, we end up with 28,800 scenarios, which is still reasonable. It's doable in a pretty short time with a modern simulator. So how do you integrate this in your test bench? Well, one option might be to use an existing UVM test bench. And UVM doesn't know anything about graphs and scenarios. But by using this interface that I showed you, when we compile our scenario, we're going to end up with just another UVM sequence. So this scenario will be implemented as a UVM sequence. It integrates with the UVM factory, and someone writing a UVM test can use this without knowing anything about portable stimulus or graphs or anything like that. It's just another sequence that you can call from your test. And it talks to the sequencer in the PCIe UVM agent. Another option might be to include an embedded processor in the test as well. And then we just throw a switch and tell the tool, okay, don't generate a UVM sequence, generate a C program that coordinates with the graph, and the C test runs on the processor and calls driver code that generates PCIe transactions. But it's the same graph, the same code. So to summarize, you're probably aware that there's work going on since more than a year in Accelera on in a working group called the Portable Stimulus Standard Working Group, and they have made some good progress. So there have been multiple contributions from both Mentor and my colleagues at Cadence and Brecker as well. So Mentor and Cadence have contributed a joint submission which includes a declarative rule-based domain-specific language, very similar to what I've just shown you here. And the goal is to, well, this has been selected as a baseline for a standard, and the expectation is to have a first version of it available sometime mid-next year. There's also a contribution that specifies a C++-based format for this, and the goal is to also create an equivalent, semantically equivalent C++ version that has corresponding constructs as the rule-based language. So to summarize here, by using a declarative graph-based method to specify scenarios, we can raise the abstraction level to efficiently capture scenarios, and anyone can review them easier than reading UVM code. And this also makes the specification portable across multiple targets, from simulation, emulation, FPGA prototyping, embedded software. So that's my final slide. I mentioned our implementation of this. In fact, that's been out there for quite a few years already. At this time, we have a couple of minutes, I think, for questions. Any questions?
Any questions?
Sergio from Huawei. Can you perhaps mention an example of an engagement you had with the customer? Which kind of, did you use it for block level or higher level, or, if you had the complete flow? And what also I'm interested is, what's the proportion between the UVM code that you're able to reuse and the code that you have to develop to apply, in fact?
So, yeah, I've been working on a lot of different applications of this, ranging from typical block level implementation in UVM test benches, where we just take out the random sequences and plug in a graph-based sequence. And in that case, little or nothing has to change in the UVM test bench. Everything else stays the same: the sequencer, the driver, the scoreboard. It's just another sequence that happens to be graph-based. I've also used, in fact, in a number of cases on processor verification, which is very different. I've developed a couple of models. One was presented at DAC last year for a Spark processor, where we used a graph to describe the instruction set for a Spark V8 processor. And the scenario was to generate sequences of instructions that exercised interesting parts of the processor. For example, making sure that all arithmetic operations had been used with all the combinations of registers at least once, and things of that nature. I've done the same thing for GPUs a couple of times, high-level models of the GPU instruction set. So this is a very high-level model indeed. But I've seen pretty much a whole range going from block level, typical, just replacing a random sequence with a systematic graph-based sequence up to these high-level models. Yeah, you were asking about changes, and in a typical UVM test bench, the only change would be to replace the sequence with a graph-based sequence. And that can be done in a number of ways. For example, with a factory override, or by changing the test to directly start the graph-based sequence instead of a random sequence. But the rest of the code stays unchanged.
How much code do you develop for it compared to the UVM?
It's usually much smaller. It's yeah. It's much more compact. It's much less to write than to write it in System Verilog. Any other questions?
Sorry. So there's one question online. How do you express constraints and coverage? Sorry, I'll start that again. How do you express constraints and coverage in the same portable stimulus description?
The constraints are very similar to System Verilog constraints. They are almost identical, so you can express algebraic relationships between different variables. You can use constructs like inside and for each to constrain things. You can specify preconditions, so if this value occurs, I want to see this other value in the next cycle, or something of that nature can also be expressed. So it's very much like you do it in System Verilog. Coverage is actually done graphically in the way we have implemented it. So you visualize a graph. Actually, it was on one of these slides here. If I go back quickly. So, for example, here in the PCIe graph, we see the graph on the right-hand side, and you see this light blue box around the instances of the TLPs and the events. This is a cross coverage, or as it's called, a path coverage. So this instructs the tool that it should systematically exercise all the different paths through this sequence that we see here. So it's actually done either graphically by adding this on top of the graph, or you can input this as a spreadsheet as well. Okay, I hope that answers the question.
Yeah, no more questions. Thank you very much. Thanks, Staffan. Thank you.